Hello there. In this lesson, we will begin our study of the Mathematics Extension 1 syllabus for the HSC Year 12 course. In particular, we will begin our study of the topic vectors with an introduction to vectors. We will look at this first dot point, define a vector as a quantity having both magnitude and direction, and examine examples of vectors including displacement and velocity. In each of my lessons, I will look to emphasize the applications of what we are studying so that you truly know what you are getting out of the course. Vectors were first used by Josiah Willard Gibbs and Oliver Heaviside in the late 19th century. They were mathematicians who independently used vector analysis to express the laws of electromagnetism. This is a branch of physics often synonymous with light, which was synthesized by another physicist, Maxwell. Since this time, their use has expanded into other areas of physics, engineering, electricity, and mathematics, among other fields. In this lesson, we begin the vectors topic. The introduction to vectors as a whole is a 6 out of 10 for difficulty. But specifically, in this lesson, we will define what a vector is and give some examples of vectors. The content for this lesson is a 0.5 out of 10 for difficulty. We will begin with this subdot point. It is explained the distinction between a position vector and a displacement or relative vector. In order to do this, we must first define what a vector and a scalar is. For those of you who are studying physics, you will most likely already be aware of this. A scalar is something which has magnitude. On the other hand, a vector is a quantity which is given both magnitude and direction. To put it simply, the magnitude of a vector or scalar is its size. But the important thing is its direction, and this is self-explanatory, it's where it is going. Now we will conduct a question to categorize different quantities as vectors and scalars. And for a vector, we will also state its scalar version, and for the scalar, we will give the vector version. But you will notice that not all vectors have a corresponding scalar. Velocity is measured in meters per second in this direction, so therefore it is a vector. The corresponding scalar for velocity is speed, and speed is just measured in meters per second. For force, we would say it is x newtons in this direction, maybe 10 newtons down, so therefore it is also a vector. There is no scalar quantity for force. For time, we would say something takes 15 seconds, but we wouldn't give a direction because that doesn't make sense. Therefore, time is a scalar quantity, and there is no corresponding vector. Distance might be the length of a cricket pitch, so it would also be a scalar as we do not give a direction. But there is a corresponding vector to distance, and that is displacement, where we would give x meters in this direction. Finally, we have acceleration. This is measured in meters per second squared in a direction as well, so it is also a vector. There is no corresponding scalar quantity for acceleration. We can give another definition of a vector, as it is used to determine the position in space of one object with respect to another. This is illustrated here on what is known as the Euclidean plane. This diagram is very similar to the Cartesian plane, but is not exactly the same. As shown here, we have 4 different lines. We have the line to A, the line to B, to C, and to D. So A, B, C, and D are all points, and they are relative to the origin at the center here. These lines are vectors. If we label the origin as O, then we can say the line from O to A is actually the vector OA. The line from O to B is the vector OB. The line from O to C is the vector OC. And the line from O to D is the vector OD. This is because we are going from O to whatever one of those points. The arrow which I've placed above the 2 letters indicates that it is a vector. We will get into different ways of indicating vectors in the next lesson. But as we can see here, all 4 of these vectors have different lengths or magnitudes and different directions. You will also notice that each of these vectors emanate from the origin. When this happens, they are called position vectors. Hence, a position vector indicates the position of a point relative to the origin. The other type of vector is a displacement or relative vector. This is when a vector originates from a point other than the origin, and it is used to show the position of one point relative to another. An example would be if we placed a point here and labelled it E, and then we had another point to here, and let's call that F. If we drew the vector EF, we would be indicating the position of F with respect to E. Now if the vectors EF and OA have equal magnitude or size and equal direction, then the point F relative to point E is the same as the position of point A relative to the origin. Therefore, EF would equal OA. So we have two equal vectors, and this is despite them emanating from different points. So what we see here is that we can have a displacement vector and a position vector be equal. Another example of a displacement vector would be if we wanted to show the position of B relative to A. In this case, we would draw a vector arrow from point A to point B, and this would be labelled the vector AB. Just as a brief preview of something we will do in an upcoming lesson, this vector AB would be the same as the addition of two vectors AO, the negative of OA, plus OB. I want you to think why this is, and in a future lesson we will return back to this concept. This brings us to the end of the lesson. What we've been able to do in this lesson is define a vector and look at position and displacement vectors. In the next lesson, we will begin the second dot point, and we will look at the different notations of vectors. Thank you for watching, and see you soon.